Hello everyone and welcome back for a lecture. So previously we have seen one design of EOT. Now in today's lecture we will discuss the another example of design of EOT crane. Okay, so let's see the given data. So given data is a lifting capacity of 150 kilonewton, then hoisting speed up to 8 meter per minute. The span means from the distance where it is has to be loading or unloading process will be happen. So span is 10 meter and the machine class is 2. So based on this data, we have to design our EOT crane. So first of all, we have to select a suitable type of wire rope, at least with the life of 12 months. Okay, so this is my first assumption. Based on that, I'm going to design a wire rope. If an example or a problem, they have specified the uh, life of wire as specified in first problem, so according to that you have to design. So material for wire, I have considered steel, which is shown in PSG. uh, that material, wire steel, with having sigma u value from 160 to 175 and 170 to 190, so higher version which we have selected. Then selecting the wire grade, bright rope wire grade we have selecting for better strength. Then lay, we are considering cross lay for proper handling, as it there is a tendency of wire rope to slide over the groove. So that's why we are considering cross lay, so it can handle it very well. So the total load on the rope is 50 kilonewton, that is a 15 ton. Now for a design load or a design value, that is shown in a square bracket of q, that q is equal to q plus a weight of snatch block assembly. That weight, we have considered 10% of total load, which is shown in PAG page number 9.11. Okay, so this consideration we have taken from that. So q is equal to 10% of q. So total load, or you can say a design load or modified load, that is a square bracket q, I say design q is equal to 16.5 ton. Now next one, selecting the falls number of pulley system, that is number of falls and bend system. So as per the India IS, if the load is less than 25 ton, we can use 4 fall 3 bend system. If load is in between 25 to 50, we can go for 6 falls. And if the load is in between 50 to 75, we can use 8 fall pulley system. So as I say, if you're using number of falls or number of bends more, it will be reduces the load per, or you can say load per fall. Okay, and it can be increase the load carrying capacity with existing system. If anyone in examination or in oral or interview, if anyone asks if you have to increase the existing capacity of EOT crane, what will be the solution? So the solution is you have to change a bending or a pulley system, so that it can be, if we are using 4 fall system, you can go for 6 fall system, so that it can increase the load carrying capacity with the existing setup. Okay, so let's go for load per fall. So F is equal to Q divided by number of falls into the efficiency of pulley and efficiency of transmission system. For mechanical transmission, we are considering 98% of efficiency, and for pulley system, we are considering, because there is a friction, so we have considered 97% of efficiency. Okay, so putting all the values, what we get F is equal to 43,393.6 kgf. So that much load is applied per fall. Now next one, selection of designation of rope wire. I'm selecting 6 by 37 for better life, as the 37 wires in one stand. It gives the better life, and it can be carry a heavy load also. So it will not fail in any sudden condition, sudden change in conditions. So I'm selecting this wire rope. Next one, we are checking the selection of rope for strength basis and for its life. So referring PhD page number 9.1, referring PhD page number 9.1, we can find out the equation over here. The equation is given where P is equal to, I just highlighting that equation. So you can refer this equation. F into sigma u divided by sigma u by n minus d by d minimum into 36,000. Sorry. I have selected wrong one. So you have to select this lower one. This lower one, not this one. En, this one you have to select. Sorry, this one you have to select. So P is equal to F into sigma u divided by sigma u by n minus d by d minimum into 36,000. So it gives the strength basis. You can find out the value of sigma u. Now here we have to find out some values, or you can consider some assumptions. Now, as we know that the n is nothing but stress factor or design factor is equal to n dash into duty factor, where n dash is a factor of safety. Okay, so we have to find out the factor of safety. How we can find out the factor of safety? Factor of safety n dash based on the class 2 hoisting application. We have considered it for crane and hoisting general block application. The value of n factor of safety is 5. So factor of safety we have considered 5. Now next one, duty factor. Duty factor PhD page number 9.2. So duty factor we have considered from this table. Okay, so based for class number 2, so class number 2 is here. Strength factor is given as 1.1.2. So it is this. Okay, so we have selected duty factor as well as factor of safety. Now next one, we have to consider the D by D ratio. Now there are two assumptions, as we said in previous problem also, based on the number of bend system. So we have considered 3 bend system, 4 fall and 3 bend system. So based on the number of bend system, you can calculate the D by D ratio is 23, and based on the ratio of drum to diameter, that is based on the class of application. So hoisting rope type, that is 6 by 37, and class 2, for class 2 it is 17. Okay, so out of that I'm selecting the 23 as the maximum D by D ratio I get. The strength will be higher one, so I'm choosing higher value of both of them. Now value of sigma u, that is 18,000 kg per centimeter square. Now putting all the values into the equation, what we find, the value of p, the value of p, what we get, 54,438.87 kgf, that is 54.4 ton. Okay, so that is the strength, so that much load it can carry. Now next one, using d is equal to 32 for p, where we pick uh, d is equal to 32, for p is equal to 58.4, referring page number 9.4, with the page number 9.4. Here, based on the load, we have recognized the diameter of the pulley. So as the desired value of p is 54, now here the available value is 55.4. Okay, so based on this standard value we are selecting, and the diameter for that is 32. Okay, so diameter for that is 32. So we are selecting diameter of the wire rope d is equal to 32 for minimum life, that is a 12 months. Now we have to check whether this mechanism, whether this uh, design survives the total minimum number of what do you say, minimum number of life, that is we have decided, that is a 12 months, it could be survive or not. Let's see. So referring page number 9.7, we have a formula, d by d is equal to m rho c1 c2 c plus c. Okay, referring page number 9.8 with the table number 3, we have calculated the value of c1 is equal to 1.16. If we want to get once again, we will go page number 9.8. Okay, so formula is given over here, page number 9.7. So this formula we are using for design for life of hoisting rope. Okay, so from page number 9.8, table number 3, for the diameter, rope diameter, it is in between 30 to 34. Our diameter is 32, so the value of c1 is 1.16. Referring table number 4, for the value of 6 c, as the strength of the rope is 180. Okay, we are using 37 6 by 37 cross lay. So the value, just a minute, show you. So we are using this one, and for this so the value of c is equal to 1.02. Okay, now next one, we have to find out the value of c2. The value of c2 is on page number 9.7 itself. It is given 0.63 to 1.15. We are selecting value of c is equal to 1, because it's totally depend upon raw material and the external treatments or heat treatment or analyzing treatments which we applied on the rope. Okay, based on that you can consider the value. So we have get all the values. Now we have to find out the value of sigma, that is a tensile strength in the rope, which can be calculated by using this formula, tan f divided by pi d square, in page number 9.7. So we have f, value of f, that is a load per fall, Then diameter we have, that is 32. So putting all the values, what we get, look at go for design. So we are referring this equation, putting all the values, what we get, sigma is equal to 13.489 kgf per mm square it is actually. Then putting the value of sigma, c1, c2, d by d ratio. Okay, so after putting out all the values, what we get, m is equal to 1.94. So the value of m, as we know that it's the value is in a hundredth. So here, this table number 1, we have to refer for the calculating the value of m and z. So the value of m is in a hundreds, so multiplied 1.94 by 100, what we get, m is equal to 194. Okay, so m is equal to 194. Now for similar point, what is the value of z now? So we have to calculate the value of z based on two equations. We can use n, or based on the working condition, or based on the value of m, we can find out the value of z. Okay, so here the value is 194. It is in between uh, in between uh, 187 and 200. So we have, with the interpolation method, I have calculated the value of z, that is equal to 326.5, because this value is in a thousands, so it is multiplied by 1000. Based on the working condition and medium duty, so we have selected working hours per day are 16 hours. So based on this condition, referring page number 9.8, page number 9.8, referring this condition, sorry, over here. So refer table number 2 for that, to calculate the value of a, z1 and beta. So as we have previously seen, it the medium duty for 60 hours per day. The value of a, that is a working cycle per month, is 3400. Number of repeated paints per cycle are 3, and endurance factor is 0.4. Just note it down, these values. So based on this, we have to calculate the life of rope, that is n is equal to 0.4 z divided by a beta z2. So putting all the values, what we get, n is equal to 31.97. That is nothing but these, that much months can be survived, and in every month we are considering 25 days of working. Okay, so based on this, our rope is safe. Now next one, selecting the standard hook and check it for induced stresses at most critical sections. Okay, so next we are designing a hook. So for hook, we are considering safe load, which we have already given. Okay, so 15 ton, and given we considering 16 ton. Okay, so referring page number 9.11, so there the standard values are also provided. Okay, so look at here, the given standard value is 16 uh, safe load. For that, the proof load is given are 32, and the value of C are varying from 151 to 131. The diameter of upper portion, that is a G1, is varying from 80 mm to 70 mm, and for that the threads are used M60 76 and M68 with the pitch 6. So we have to select any one of them. Okay, so let's see. Okay, so we have considered proof load is 32 ton with a material of C55 CR75 referring PSG. Um, for that, the yield strength is equal to 660 megapascal with a factor of safety 3. So the design stresses we can calculate it. So tensile stress design sigma t 660 divided by 3, that is 220, which is equivalent to the design bending load. Now value of tau that is a shear load. So it is a half or 0.5 times of tensile strength or bending strength. So that is one half of design sigma t, which is equal to 110 megapascal. Then crushing load, that design crushing load is the twice of sigma t, that is design sigma t, this is 440 megapascal. Okay, so look at the hook section. There are three critical cross sections. So first one of one, which is goes purely or you can say first one, it is purely loaded with the bending section. Then two, it is pure tensile, and third, it is also pure tensile. So we have to consider these load carryings, or you can say additional loads, so that we have to select a cross section. uh, in a previous design we also discussed about the cross section as the inner fiber, you can say the so this one is the inner fiber and this one is the outer fiber. We have select a trapezoidal cross section with the more thickness we have referred to the inner fiber and lower thickness we have referred to the outer fiber. We can go for a square section also, but it can increases the weight. We can go for rectangle, it is similarly increases the weight as the inner fiber carries a heavy load, so that the thickness of the inner fiber should be high, and outer fiber carries purely compressive loads, so the outer fiber thickness should be as minimum as possible, so that the weight as well as strength criteria, both criteria can be satisfied properly. Okay, so let's see with the design. uh, okay, so for that referring, go with the PSG. Okay, so we are selecting the value of C is equal to 151, so that the value of G is 80 and G1 is equal to M76. Okay, so according to that we have all values for different cross sections or different parameters. So A is equal to A is equal to 2.75 C. According to that you have to find out all the values of the um, related parameters, so that you can easily find the uh, curve beam value, what is the radius of curvature which we needed for further calculation. Okay, by using this one you can find out the all the dimensions. Okay, let's go for with the design. Okay, so in a design I have calculated everything is over here. So based on the given standard formulas we have calculated. Now next one, by considering the cut section 1 or you can say the critical section of hook can be approximately considered as a trapezoidal cross section. For that we are referring PhD page number 6.3. So here the PhD page number 6.3 is given all the values required to calculate value of distance from the center of curvature to the neutral axis and the distance from the center of curvature to the centroid axis, that can be calculated by using these two formulas. I request all of you draw this diagram in examination also and whenever you are going for design, because it indicates how you can calculate it and from which area or from where your center axis of curvature is lies. Okay, so it will give a proper idea to the examiner how you have considered the design. Okay, now go to the design. Okay, so whatever the needed values I have calculated, and I have written the empirical relations which can match with the given value. To calculate the BI, okay, internal thickness, you can directly consider value of M. To calculate BO, you can directly consider the value of Z. Small h, that is a height, h is equal to, you can consider capital H. Okay, Ri is equal to C by 2, Ro is equal to H plus Ri, E is equal to R capital R minus Rn, Hi is equal to Rn minus Ri. So these are the empirical relations which I have calculated or found from the comparison. Okay, you can refer and you can use these direct empirical relations so that you can save your time in design. So the area of cross section which is given in PhD page number 6.2, A is equal to 0.5 Bi plus Bo into H. So putting all the values, what we get, A is equal to 7633.77 mm square. Rn is equal to 1 half Bi plus Bo into H divided by BiRo plus BoRi divided by H, natural log of Ro by Ri minus Bi minus Bo. So we have all the values now. So putting all the values, what we get, Rn is equal to 120.6 mm. Now calculate the value of capital R. R is equal to Ri plus H by 3 Bi plus twice of Bo divided by Bi plus Bo. So value of R, capital R is equal to 130.11. Now we have to check whatever the stress induced and whether it is safe or it can be failed. So tensile failure of cross section 1 1. I request all of you to make some changes. We are checking the it is the cross section of 2 2. It's the upper portion of hook. Okay, we are considering this cross section. Okay, for first safe condition, we are considering this cross section. Just make a modification in the right over here. So sigma t is equal to sigma q divided by a. We have a cross sectional area. So 150 into 10 raised to 3 divided by 6733.77. So what we get, induces tensile strength is equal to 19.64 megapascal, which is far or which is very less than the design one. So our design is safe for first condition or first section. Now considering cross section area 1 1, which is very critical and very important to design. That is that is, I just show you. So this one is the cross section area 2211, where the maximum load is carrying. It is a purely bending failure because inner fiber carries tensile strength, outer fiber carries maximum compressive strength. So ultimately it is a compressive tensile, so it's a bending. So sigma b max is equal to mbhi divided by aeri. So maximum bending stress we can calculate it. Sigma b is nothing but q into r. So uh, putting all the values, what we get, the maximum bending stress is 160.58 megapascal, and which is less than the design value. So our design of selection of the trapezoidal cross section is safe. Now tensile failure of section 33, again you can modify this value. Okay, we are considering this cross section now. This is a very important cross section. Okay, so in this cross section it is directly tensile load, because it is directly contact with the load. So that's why we are considering a direct tensile over there. So sigma t is equal to q by pi by 4 dc square. So diameter of the uh, एक minute, sorry, we have considered above diameter, sorry. So previously we have considered that one. Now here we are considering this sigma section 22, which is in a diametrical form. Okay, so please make a correction in that. So diameter we have is a 70 mm, which we have already chosen from standard value, page number 9.11. Uh, so putting all the values and calculating the induced tensile stress, that is 38.97 megapascal, which is very less than the design one. Okay, so till date we will discuss the design of rope. We have checked the induced stresses, we have checked the strength, we have also checked the life of rope. Then we are going with the design of hook, where we are selecting the cross sectional area. We have find out the empirical with by using the empirical relation, we find out the dimensions of the hook. Also we have checked calculated the neutral axis lengths, uh, then curvature beam lengths, and calculated check whether the three cross sections of the hook are satisfying the criteria or not, or whether they can able to carry load or not, and hence we are found that the hook is safe with the all most critical cross sections. Okay, so till time we have stop over here. In next design we will discuss the further things. Thank you. If you have any query or any questions, you can personally call me. Okay, thank you.